meeting, it seems like it's a really nice idea to try and sort of give a state of holographic duality with all of the signs of the cosmological constant. And let's hope that through these panels and maybe also the Gather Town, there'll be lots of interactions also between people who seem to have specialized or mainly specialized on one particular sign. So this panel discussion indeed is one for the original case with the negative cosmological constant. And the way that it's going to work is that all of the panelists, me included, will talk a little bit about some perspective that maybe they in particular want to emphasize. And of course, I would say that we can welcome questions also during those presentations, but of course, you should always keep in mind that if you want to have a longer discussion or raise a comment or a particular question, that there will be plenty of time to discuss on all aspects after all the four presentations. So with that said, I'll go first. And I decided that what I want to focus on is a particular issue that has recently come up in ADS-CFT, rather than trying to give a big overview. And I think anyway that, you know, across all four panelists will have a nice diversity of topics. But before I go to that issue, of course, I should just say, I mean, first of all, there was already a very nice review by Tom Hartman, who made many of the points that I would like to revisit already very nicely. But he also introduced, in some sense, you know, the arena. But let me just say, nevertheless, that ADS-CFT for the negative sign of the cosmological constant, as probably everyone in the audience knows, is supposed to be an exact duality between, on one side, quantum gravity, oops, just delete, I wanted the point, okay, quantum gravity in asymptotically ADS space in D+1, and between a CFT in D dimensions on some manifold that we can choose, that is, in this case, isometric to the boundary of this ADS D+1. But two things to say there is, of course, that first of all, saying quantum gravity in asymptotically ADS D+1 space, I mean, whatever that is, we have some explicitly known examples where, for example, this becomes something like string theory in ADS D+1 times some compact space with a very specific spectrum and very specific rules to calculate. But we certainly, most of us believe that this is a case that is more generally true. And if it is more generally true, then we really have to, in some sense, admit that we don't know exactly then what we mean by quantum gravity in ADS D+1 space. So this is part, in some sense, of the interesting open questions that we try to answer. And I suppose we try to answer it by working on specific examples and maybe extrapolating to what the general story is. And the other comment is that once I've said that it's exactly dual to a CFT on some manifold that is, you know, for us to choose, then in some sense there is the statement that in this sense the theory obviously must be unitary. So you know, this CFT in some sense obviously is unitary. If it were not unitary, we would be extremely surprised and we would be contradicting, you know, a lot of things we know about quantum field theories. And so in some sense, whenever we start talking about unitarity issues, and I will do so, and I'm sure my co-panelists will also do so, there is in some sense a way in which obviously the unitary problems are solved. But that's not particularly useful, as we will make the point. I already mentioned this, but just by way of introduction, of course, nowadays ADS-CFT is really a rich and vast field, but there will certainly not be time, even on a 2-hour panel, to delve into all the interesting aspects. So we'll be focusing on exciting progress on precisely issues that address this apparent conflict between unitarity and gravitational theory. And so we will look at recent exciting progress on quantum black holes. So in principle, these unitarity issues immediately are solved because of this obvious statement that the dual theory is unitary. But in practice, it's actually not very helpful to say it, because we need to ask in particular how this works in the bulk and how it works in detail. And one such resolution that works at quite a fine-grained level of detail is basically the one that's related to what I like to call order from chaos. So this is a relation between quantum gravity and quantum ergodicity. And since, well, we are virtually all in Prague, I chose to illustrate this idea. We all know this idea. I think it is actually comes probably from the Greeks, but it's usually thought to be a biblical idea, that at the beginning there was chaos. And this is here represented by a woodcut by Wenceslaus Holler, who lived in Prague from 1607 to 1677. So this represents this idea of the Greeks that somehow what underlies everything is the void chaos. Well, symbolically, this is kind of the point that I want to make. So what is this unitarity issue? Well, of course, the famous formula by Bekenstein and Hawking of the black hole, which tells us that the black hole entropy is proportional to the area of the black hole in units 4GN. This for a black hole of interest is finite. This is a finite entropy. So within ADS-CFT, this allows us to basically pose very sharp questions about signatures of unitarity or lack of unitarity in such quantum systems, because we now want to discuss at least a sector of a dual unitary theory that has a finite Hilbert space, and that basically satisfies the basic rules, all the normal rules of quantum mechanics. And so let me introduce very briefly some sharp signatures of the lack of unitarity in such quantum systems. I'm sure that many of you have seen them already, but I want to put them into a light of the idea of ergodicity and quantum chaos. So of course, there will be signatures in, let's say, some fairly ordinary objects, such as the two-point function with respect to a density matrix, which can be either, let's say, the canonical density matrix. It could be, e to the minus beta h, but we could also think about it as a density matrix, as a density operator that comes from some pure state. In both cases, there'll be interesting things to say. So this will have some unitarity issues, in particular at late times, if calculated from gravity. But perhaps a cleaner probe of the same issues in some sense is the spectral form factor. The spectral form factor basically isolates the phases that I have. If I look at the Heisenberg operator time t, I have some phase evolution. And if I look at the canonical density matrix, I will have a factor like this. So this, in some sense, is a quantity that will give us a very sharp unitarity signal. And I just wanted to introduce it at the risk of boring some people who have seen it many times. Now, you can think of the spectral form factor, temperature beta and time t, as being basically two copies of the partition function. Tom referred to this as ZZ. So this is Z at an analytically continued temperature beta plus IT times its complex conjugate. Okay, and so the kind of games one will play now is we ask for long time constraints of this spectral form factor. And the simplest one that we can think of is by asking what is the time average of the spectral form factor across some long time interval, capital T here, okay? So for a sufficiently generic system, which doesn't have a macroscopic number of degeneracies in its energy eigenvalues, this basically projects onto a partition function at temperature 2 beta. And in particular, this quantity is always positive. And if you do the counting, as such, it's of order e to the entropy, right? There's approximately e to the entropy states that contribute significantly to this kind of sum. And so we can estimate this to be non-zero and of order e to the s. The way that this is usually shown is actually that you normalize it by the square of the partition function. And in this case, the counting gives you one factor of the partition function versus two factors in the denominator. So the whole thing will be non-zero, but it will be e to the minus entropy. And so this is in stark contradiction with what semi-classical gravity would have you believe, because if you calculate this, essentially you calculate it by calculating the semi-classical partition function of some black hole, you will actually find that this is strictly going to 0 at late times. So it is immediately in a contradiction. However, we said that it cannot decay to 0 at late times. And so maybe it's a good idea to ask what actually is the reason that it doesn't decay to 0 in these quantum systems. Well, the reason is that what remains at late times, so this is, this ZZ, particular the log, is a function of logarithmic time. In particular, what happens is that at sufficiently late times, namely after a time scale that one might identify with what's called the tauless time, there is some irreducible quantum noise. The system will become very erratic. There is some quantum noise that remains in the system, and that on average approximately is of size e to the minus the entropy of the system. And so somehow the semi-classical gravity precisely misses this irreducible quantum noise. I've said this for reasons of convenience for the spectral form factor, but a very similar story can be told for the two-point function, okay? So the question that I would like to ask is, what is actually the bulk description of this quantum noise? And again, in an attempt to connect with the virtual location of this conference, this is actually a little bit like the story of Rabbi Löw here and the golem, because if you start, reconstructing this quantum noise, which is supposed to help you to find the truth of what's going on at late times, you will find that this actually raises an extremely interesting, extremely complicated puzzle that we didn't previously appreciate. So in some sense, the old story of, I don't know, Frankenstein and so on, you create a monster that in the end you can no longer control. Well, hopefully maybe we can control it, but for the time being, let me tell you what actually is this monster that comes out when we ask about the quantum noise. Well, for example, in JT gravity, so a two-dimensional example, this quantum noise, the average of this quantum noise can be traced to non-trivial topology spacetimes, which basically have one boundary for each copy of the partition function, or equivalently the density of state, which have a connected contribution. There is some connected contribution between two boundaries, which represent rho of E1 and rho of E2. And this wormhole is precisely the fact that there is some non-trivial correlation that comes from the spectrum of these theories. And this non-trivial correlation is quantitatively able to actually reconstruct the average signal here. So let's say, for example, to be precise, it is able to account for the fact that this is non-zero in order e to the minus s, so it captures some aspect of this quantum noise. But at the same time, it poses the problem that, well, if I just take the product of two partition functions in an ordinary theory, then this is obviously equal to a product z times z star. And it does not contain something like a non-factorizing contribution like this. The only context that we know in which such a non-factorizing contribution actually makes sense is if you do some sort of ensemble average of theories. In this case, you're allowed to have non-vanishing correlations of this kind. So I should probably have said connected. It's important that these are connected correlations. So somehow the monster that we have created is an ensemble. The question is gravity, for example, in ADS, really an ensemble? Well, there are certainly two options, maybe more. You could say yes, this symbol here really is like a random matrix average. This really is an average. Or you could say, in fact, no, I would like to insist on the fact that there is one bulk and one boundary, but then we need to make sense of this symbol here. So this means that we say that no, this is actually just an effective description of some universal quantum correlations. And I want to propose that this has to do with quantum chaos. So I will use my remaining 5 minutes to say a little bit more about this. And I want to make the point that there is something universal going on. And I want to suggest that the fact that something universal is going on, it is very natural to think about this universality, as I think even Tom already suggested, in some sense of universality classes, which should be related to some idea of symmetry breaking. So some comments. So this option 1 really is a radical departure from conceived notions. You know, we didn't think of ADS-CFT as being a duality between some ensemble and one gravity theory. And one might even ask, is such an ensemble interpretation even possible in higher dimensions? So is there something like a higher dimensional version of random matrix theory that is even a candidate for making this story possible? So that's one of the questions we might even want to talk a little bit about. But the option 2 raises the question, why or how does semi-classical gravity know so much about something? So these quantum chaotic correlations will after all come from having two times a copy of this discrete spectrum and looking for signatures, subtle spectral correlations that are induced by quantum chaos. But why should semi-classics know anything about the sort of information of discrete energy levels or some effective information of discrete energy levels? That's certainly a very disturbing question that is raised by option 2. So let me just, for sake of discussion, raise a possibly likely scenario. And of course, as you might expect by now, I'm linking it to another celebrity in Prague. This is a depiction of orbits due to Tycho Brahe, who, by the way, also had an interesting relation to this Rebbe Löw, but let's not get into this. However, so these are some periodic orbits that were determined experimentally by Tycho Brahe using his observatory in Bohemia back then. So what I want to say is that one way in which this unreasonable effectiveness of semi-classics is quite natural in the context of quantum chaos is what is known as periodic orbit description. So there one would propose that semi-classical gravity is the periodic orbit description of the universal quantum chaotic dynamics of some underlying UV quantum gravity. So what do these words mean? Well, I can say a couple of things about that. So the orbits come in because what we do is, let's take our favorite quantum chaotic system, for example, a nucleus. This has been mentioned before. And let us write the density of energy levels by using the imaginary part of the propagator. There's nothing particularly interesting here. But it becomes interesting once we actually evaluate this propagator using semi-classics, just standard semi-classical evaluation of this propagator. I believe it goes under the name of the Van Vleck propagator, but it's just semi-classics. Then you can actually show that this orbit sum, this rho-rho correlation ends up being a correlation between a sum over periodic orbits. So one identifies a subclass of orbits and phase space of the system. These are the so-called periodic orbits. And one has one sum for each of these insertions of rho. And then what one does is one says, well, of course, this is automatically factorized because it's one expression times another expression. Let's write it like this. Sorry, it's actually rho times rho. Yeah? But if I introduce a little bit of uncertainty in the energy, so I average this over energies in one given system. There's no ensemble here. I have one quantum chaotic system, but I average over some small energy window. It is actually known that in controllable quantum chaotic systems, so not yet gravity, okay, I can basically reconstruct the details of this average signal. In particular, I can get out the ramp, so this linear rise. This is known as the Berry diagonal approximation. And I can even, in some cases, get the plateau. And I say in some cases because it's more of a technical problem, maybe not a conceptual problem. And reconstructing the plateau from these periodic orbits goes sometimes on the name of Riemann-Siegel. Sometimes it's quoted as the Altshuler-Andreev instanton. So I've just said that basically you can get the diagonal approximation, you can get this, and you can even sometimes get the plateau. And the analogy that one would make, which comes with a little bit of evidence, is that this diagonal part is sort of like the wormhole, and the off-diagonal parts are there are interesting subtle off-diagonal correlations between orbits. These give you the plateau, and moreover, you can think about the fluctuations in this context. But what is interesting is that there is a framework which works in controllable quantum chaotic systems, which indeed reproduces details about the discreteness of the spectrum just from semi-classics. Okay, so there is a precedent in which this works, and so let me skip this for a second. Let me just say that in other words, if these wormholes and baby universes are like the periodic orbits of quantum chaos, then the question is of which theory are those gravitational solutions, the periodic orbits. So for sake of discussion later, I mention here string field theory, but we can talk about it. Let me just mention two more things. So what is this delta E averaging? Well, first of all, it means that it's not really a fundamental property. We're not saying there is an ensemble. Okay, this is a technical device. And it's a technical device that is needed to define level statistics. So if I look at one quantum system and I want to ask about correlations between levels, then I need to draw some histogram, which I indicate here in gray. So I need to define some bin width. And in this bin width, I sample energy levels. And from this sampling and some limiting process, I can actually extract some smooth function, which gives me the level correlation. Here I've written the famous Wigner surmise P of omega, which is basically the probability of finding two energy levels a distance omega apart. And it's usually convenient to measure omega in units of the mean level spacing. Now, I'm almost at the end, so I would say that conceptually this idea is not very different from what also ETH does, right? It tells us also that maybe not one quantum system, but one pure state can look like an ensemble average. So here in the RMT sense, in the quantum chaotic or ergodicity sense, I say one theory can look like an ensemble of theories. Okay, and there's a controlled way of understanding it. In ETH, I say that one state, in some sense, subs in extremely accurately for an ensemble average. And I believe that Jamie will have a lot more to say about this. So let me conclude then by some things to ponder, which we can get to later. So I would like to ask the question, for example, do we actually have concrete evidence that gravity must be thought of as an ensemble? Or is it in fact true that everything that we've learned so far, and this is certainly the opinion that I want to advance, is compatible with either this ETH idea or this ergodicity idea? But I'd be interested even also to hear the audience's thought if there is actually a smoking gun that really tells us otherwise, maybe in low dimensions, so maybe in JT, maybe in ADS3 gravity. That's certainly something we could discuss. So then if what I say is true, the question is semi-classical gravity's role really just to compute the detailed statistics of a pseudo-random signal? So it allows me to say that the signal will be pseudo-random and it will have a certain statistics, certain moments. Is semi-classical gravity's role to compute this? And thirdly, are there even candidates for higher dimensional versions of such RMT ensembles which maybe I should have put a second point, because in some sense it's the converse of question 1. So if question 1, you know, if the answer is yes in lower dimensions, we still have to work against the problem that in higher dimensions, we don't really know of good examples, even what these ensembles could be. So, right, so that's what I had to say. And I propose that we get back to these questions and those of other panelists later, and I will now cede to, I think, naturally, it would be Jamie who goes next.
Great, let me just pull up my slides. Okay, thank you for the invitation to participate in this panel. Let me continue more or less where Julian left off. So if we're talking about you know, gravity, a negative cosmological constant, then most of the last, oh, it's not actually, my slides are not moving. There we go. You know, for most of the history of ADS-CFT, we've sort of viewed the problem like this, you know, on one side, trying to better understand the, say, a CFT partition function, and the other side, trying to understand how the gravitational theory fills in that information to give us the same answer. Of course, it's been in the last couple of years that we've understood that there's also another very interesting thing to calculate in this duality, and that's understanding products of partition functions. In the CFT, this is not a very interesting quantity. It's just a product of some number. But of course, in the gravitational theory, when we do this calculation, we find much more interesting contributions, not only the ones we naively expect, but connected contributions that seem to ruin the factorization of this problem. And so if we really believe that these connected contributions are real and meaningful and don't sort of disappear or cancel from this calculation, then we're left to wonder how we understand this quantity, this product of gravitational partition functions. How do we understand the fact that there seems to be some sort of non-trivial correlations between something that we might have naively thought was just a number? So we ask, what does the sort of angle bracket mean? There's a few obvious answers. The first is that we should interpret it as some sort of ensemble average, where we average over theories or average over sort of microscopic couplings in some quantum theory. Another very interesting proposal is we should think about this really as sort of a standard expectation value in some sort of third quantized baby universe Hilbert space. And a third option is that this bracket really is just some coarse graining, where we have some single unitary quantum theory, and we're just averaging over some microscopic details in the calculation that our effective field theory doesn't see. The first two of these, on the ensemble averages or expectation values in some baby universe Hilbert space, I think it's fair to say have received a great deal of study and attention in the last couple of years. And today, I'd just like to take a few minutes to advocate first that we should spend maybe a little more time thinking about this third option, that we can understand these contributions to the gravitational path integral by coarse graining over microscopic details in a single theory. I think it's fair to say that this is the most conservative of these three options, because usually, although certainly not always, we think of gravity as some effective theory and not a microscopic one. So that's not to say that we don't believe that there are sort of microscopic UV complete theories of quantum gravity, but I think in almost, you know, in the sort of paradigm where we think about sort of a bottom-up large CFT, I think it makes more sense there to think about gravity as merely being an effective description, which may or may not have some completion in the gravitational language to some UV complete theory. Or that is, so it always does have some description as a UV complete theory, but maybe not in the gravitational language, then perhaps the only way to think about that as some complete theory is really in the sort of dual CFT language. And the other point is that we already often think about space-time area as being average coarse-grained description of microscopic states. You know, when we take, say, some area of some region in space-time, you know, we've learned that we should think about this as some entropy, perhaps some entanglement entropy. So that's counting some coarse graining of microscopic states. And we already think, you know, if we here, let me draw a spatial wormhole. So I've made it kind of thinner than the sort of space-time wormhole pictures we often draw now. You know, the space, just the regular sort of spatial wormhole in a thermofield double really is some geometric connection that we understand is built out of, you know, averaging over microstates in the theory. That's not to say that, you know, coarse graining it should be thought of as the only thing or the only possibility of that. So I think coarse graining is all one needs to understand the emergence of these Euclidean wormholes and interesting contributions to the gravitational path integral, but that doesn't mean, you know, it's the only possibility. So when we still know there's a duality between JT gravity and random matrix theory, and there are, you know, simple toy models of gravity that are described by this baby universe Hilbert space. And so I think one of the interesting challenges is that, you know, given an effective gravitational theory, is to ask what type of ensemble or what type of coarse graining is consistent with that theory. And are there useful sort of discriminants or observables, things we can calculate in that gravitational theory to give us a clue or to constrain what types of dual ensembles it could be equal to. And then another challenge is to understand that if we have some fixed microscopic theory, what can we add to this effective theory to make our gravitational description UV complete so that it's factorizable to sort of remove these correlations between things that really should just be numbers. And you know, given some effective gravitational theory, is it always possible that there is some reasonable set of objects that we can add to the theory, or is it that the only, typically that the only factorizable UV complete description is really the sort of the dual CFT description? I don't think we understand very much at all about the first question. There's definitely been a fair amount of work already trying to understand how we, you know, what we can add to the effective description to restore factorization. I would like to just spend a few more minutes thinking about what types of coarse graining could give rise to these Euclidean wormholes. And so when we think about coarse graining as, you know, high energy theorists, usually, you know, to us, an effective field theory is usually some description of, you know, when you're doing low energy experiments near the vacuum. And so the very natural thing we're used to doing when we talk about coarse graining or renormalization is integrating out large energies. You know, integrating out energies much greater than the types of physics we're interested in studying. But in gravity, you know, we're very often interested in high energy backgrounds. You know, we want to study, you know, large black holes. On the other hand, you know, these black holes also have exponentially dense level spacings, you know, they're e to the minus c type splittings in energy. And so I think a natural coarse graining, if we want to understand gravitational effective theory, is really to integrate out these level splittings, that is, integrate out large times instead of large energies. And even without some rigorous framework for how to do this, or some sort of precise prescription for what this renormalization would look like, you can see very easily that it generates all of the interesting phenomenology of Euclidean wormholes that one would want to, that one has seen from sort of the ensemble of theories picture or from the baby universe picture. So just to give just a very quick picture for how that works, you can imagine just say taking in your effective field theory type description, some state it's meant to be, say, at some energy E. And you can think about that effective field theory is really describing just some sort of random state in some small energy window, some sort of energy bin around that energy in the microscopic theory. So when you calculate overlaps in your effective field theory description, say between two states at the same energy, these are two sort of independent states, then you find that on average, their overlaps are 0, of course, and you can go and calculate, say, their norm squared and find that there are, e to the minus s corrections. So they're mostly orthogonal, but they have tiny overlaps with each other. And you can use the same type of just very sort of naive coarse graining, this naive effective field theory, to go and sort of reproduce the, all the interesting calculations you would want. So if you want to go and take a density matrix built out of these sort of random states, and you can go, say, compute the second Renyi entropy, and you find that you get both disconnected and connector contributions to this calculation that look a little bit like, the disconnected typical gravitational solutions and some sort of wormhole contribution. And they do exactly what you'd expect. They show that the second Renyi entropy increases for a while, which is described by the disconnected solution, and then turns over and sort of unitarizes, which is the contribution of the wormhole. Or you can do a calculation where you try to compute in the effective field theory the product of two partition functions, and you find that not only do you have, say, a disconnected contribution, but already in just a sort of very naive coarse graining, you find lots of connected contributions that link the operators in the two theories together in various sort of forms of traces. And so, again, you have this sort of microscopic calculation, and then you have some sort of rough gravitational pictures of them, where you have, products of disconnected geometries and sort of Euclidean wormhole type contributions. Although these are, the gravity here is in quotation marks. There's no real understood gravitational description of these contributions. These are just sort of schematic ways of understanding what they can contribute. Just want to make a few comments. The connected geometries you get in this way are sort of non-geometric wormholes. So if you viewed these path integrals as preparing some entangled state between the left and right in this theory 1 and the left and right in theory 2, then sort of no matter how you divide up the system, all of the entanglement entropies are just order 1. So if there's such a thing as a priori they don't give some sort of geometric wormhole. Of course, you may want to ask in these types of coarse grain theories as well, is there some way that you want to rearrange these contributions as some sort of sum of other contributions, where you might think of them as some sort of constrained picture, like a constrained instantons one sees in gravity. Another thing is that you want these geometries to be connected in the infrared. When you write down the sort of naive thing you get in the quantum theory, it looks like they're sort of joined together in the UV, that you have things that are linked together in traces. And so it looks somehow like their boundaries have been joined together. But you can sort of rewrite these things in some interesting way, where the types of correlations you get between the two theories, you can get by sort of breaking them apart into the two traces you started with originally between a left theory, so theory 1 and theory 2, and then inserting some sort of entangled projectors, which sort of are how you sort of link the two theories together. So you sum over a whole bunch of projectors in the theory that link them together. These contributions, e to the minus beta h, are typically the things we normally think are there that are giving us partition functions. They're the things that sort of meant to live in the UV boundary of our gravitational theory and define our sort of boundary conditions in the UV that tell us the gravitational calculation we're doing. And these other contributions that sort of tell us how to link the theories together, so how they're correlated with each other, perhaps we want to think about as some infrared boundary condition we've inserted into our calculation. And so I think an interesting question is maybe how do we, or can we understand a sort of infrared boundary conditions in gravitational theories, that simple operators we insert in the partition function should be thought of as things get inserted at the UV boundary. So e to the minus beta h is some simple boundary condition. But these very complicated microstate projectors are, they don't live naturally at the UV boundary. They live somewhere here in the infrared, and they tell us how we really want to sew our calculation together. So this sort of very schematic, naive view of coarse graining can give us the phenomenology we want. But I think a very interesting question, if one is going to go in this direction, is to ask how to make coarse graining into a precise renormalization scheme. One way to do it is sort of the typical effective field theory language, where you sort of work from the bottom up. So you write down the most general effective field theory consistent with the symmetries of the problem. And I think this sort of leads you to the picture that Julian and his collaborators have been working on. you identify the symmetry and the symmetry breaking in the problem, and that tells you how to write down your theory. And so perhaps this type of bottom-up symmetry breaking picture sort of telling you about how what's going on in the infrared of the gravitational geometry. So how two theories get sewed together in the IR. I think, but another interesting way to think about this problem is just from the top down. And this one, in this picture, one's not just identifying the symmetries of the problem, but really trying to explicitly integrate out degrees of freedom to arrive at some effective theory. This picture, I don't really understand how to meaningfully do this, although certainly some people have started thinking about this problem. One possibility I'd like to suggest as something interesting to think about for how one might integrate out the level splittings is not just to think about the level splitting themselves, but to think more about complexity. So I think there is this very nice picture that's been developed by many, many people, but let me just sort of give some sort of naive cartoon. We think if we sort of take, say, the thermofield double state and evolve it in time, we can think about it as some growing quantum circuit. And it's believed that the sort of growing quantum circuit, which describes, say, the time evolution of this state, is meant to have some connection to the sort of interior infrared geometry of this state. So here, it's thermofield double state, and as we time evolve, we're meant to see, say, the growing of some maximal volume slice in the interior of a black hole. So one thing that we could do is use time evolution to build some basis of operators in our theory. Say we take some operator and evolve with, say, take the commutator with the Hamiltonian and take the commutator again and keep taking nested commutators with that operator, develop some basis of operators. And thinking that, each of these operators in this sort of long chain of operators are growing more complex. So operators that are just a few commutators of H are quite simple, but those that have many, many commutators of H are very complex operators. This is an idea of complexity called K complexity. So complex operators, at least in this K complexity picture, but I think maybe more generally, no matter how you want to think about complexity, sort of necessarily oscillate very rapidly in narrow energy windows. And are reached here sort of explicitly by long time evolution, that a very complex operator is some very large nested commutator, very, very sort of large nested commutator with the Hamiltonian. So it's very sort of like a long time object. And so there's some well-defined sense that if you integrate out these large complexity operators, you're really sort of coarse graining some discrete spectrum and replacing it with some sort of continuous approximation. And so a question that I would also like to raise is, perhaps if we're thinking about how we coarse grain some gravitational theory in the way I'm suggesting, that it might be interesting to think about a coarse grain scheme that not just integrates out long times, but really is integrating out complexity in some interesting way. So let me stop there.
Thank you very much, Jamie. Extremely interesting. I already have several things I would like to discuss with you about this, but I think that we would just proceed unless the audience has some questions at this point, just clarifying questions. Longer questions, I would say we'll just postpone to the discussion. Okay, yeah, so I also think it was very clear. So I think we decided that Daniel, you would go next, is that right?
Yes, I think so. Oh, sorry. Okay. Yeah, I hopefully, when I share my screen, my computer won't get weird, which once in a while it does with this particular machine. Hopefully that's. Okay, it got a little weird, but if it looks okay on your end, it's okay for me.
It looks fine for me, and I think that means for everyone else too.
Great. Yeah, maybe I can just make it full screen. How do I actually do that? Okay. Oh, sorry. Wow. let me. Oh, I can't mute myself. Okay, great. That's okay. Okay, so I have not that many slides, but what I thought I would do in my little time to speak here, and by the way, thanks for the invitation to speak on this nice panel, was just to pose 3 questions in ADS in the context of anti-de Sitter space, which I think if we knew the answers, it would tell us something that, could hint that how we would understand quantum gravity in other situations, like in de Sitter space, like our universe, and so on. So the first question I wanted to ask is kind of closely related to what Julian and Jamie talked about, and maybe I'll also make a few other comments related to what they were saying. So, but I wanted to describe it sort of a similar physics, but from the Lorentzian point of view. So let me start by saying there's kind of an interesting puzzle that we don't always discuss, or we didn't always discuss perhaps as often as we should, related to the black hole information problem that we might just call the entropy puzzle. And this is the fact that semi-classical states that are in the domain of validity of the bulk gravity effective theory. So there's the effective theory of gravity coupled to matter, whatever it might be, or the low energy limit of the full string theory. Those semi-classical states already overcount the entropy, the Bekenstein-Hawking entropy. So in particular, if you look at a black hole state that's formed from collapse, and we try to discuss the geometry along some spatial slices. Of course, to do that, you have to fix the gauge in some way. One convenient way of fixing the gauge is to demand that the extrinsic curvature of the spatial slice is 0. So that's a maximum volume slice. So let's have that in mind. Locally, that fixes the gauge. That is the temporal gauge, like local diffeomorphisms. And if I look at those kind of slices, then the size of the interior grows linearly in time, at least after a while. And sometimes the size of such slices was identified with complexity by people like Leonard Susskind, collaborators. But here I'm not going to focus on this complexity question, but something in a way simpler and more primitive, which is just that once you start discussing states, so we can think of a problem. We just have an initial slice, the size is some L, and then there's various matter configurations, all with a long wavelength, so that it's definitely in the domain of validity of the bulk effective theory. There's no, UV modes who we might not understand involved. If you just try to count those states, once the size is bigger than some amount, it already beats the Bekenstein-Hawking entropy that you would compute by assigning, the 1 over G Newton times the area of sort of the bounding surface. So, from a very coarse point of view, the entropy of matter configurations on slices of size L is proportional to L. It's sort of like the effective central charge of the matter theory times L, roughly. And we can even try to compute the naive count of such states by doing a Euclidean path integral. So we could take here in this trumpet-like picture, the line on the wiggly boundary on the left is supposed to be an ADS boundary. And then the green boundary on the right is some interior of the configuration where the horizon doesn't shrink to 0. So sorry, where the, some interior of the configuration where the Euclidean time circle doesn't shrink. So these are configurations unlike the Euclidean black hole where the Euclidean time circle shrinks in the interior. This trumpet thing is counting, configurations that, respect the time slice, right? So if you take a slice here, it looks like an ADS boundary, some boundary in the interior, which could be a place where, say, the horizon manifold shrinks. That would just be like the origin of polar coordinates, or maybe it's some end of the world brain. It depends. That will depend on the specific setup. But the important part of this picture is just that the Euclidean time circle won't shrink. And then if you compute Euclidean path integrals like that, the answer is actually just simply divergent. And the divergence comes from the region where the length of this cycle here, the length between the distance between the ADS boundary and the green line grows to infinity. You're supposed to path integrate over everything. And the ones where that's extremely long are basically computing the thermal partition function of the matter theory and at very high temperatures. The reason why high temperatures is because there's a huge redshift factor between the end of the throat where the green line is and the ADS boundary. So the point is, like, these are basically the Lorentzian descriptions configuration, which looks kind of like probably they have horizons in Lorentz signature. They have an extremely long throat, which eventually ends deep in the interior of the black hole. It's like a bag of gold spacetime that general relativists sometimes discuss. So those things have a huge entropy. And as the interior grows, the entropy is bigger and bigger. If you try to compute the total entropy of them, you get infinity because the interior can be arbitrarily big. And all of those states are in the domain of validity of the gravitational theory. So there has to be something that gets rid of these states. So, you know, sometimes I think in discussion of, well, maybe I'll come back to that in a second. So if you could resolve, maybe one point is if you could resolve the entropy puzzle, you automatically resolve the black hole information problem, because, you know, in the Hawking's computation, let's say we improve it by computing all of the perturbative corrections and so on. So we're not just doing Q of T in a fixed background, we do the exact calculation if we could in the low energy effective theory. You find pure state, of course, after, say, the page time or some time when the black hole starts to be mostly evaporated, the state looks pure. The reason why Hawking get a density matrix is because, of course, at the end, you trace over the interior, because when the black hole is mostly evaporated, it's not supposed to have a big entropy. It's supposed to be bounded by the Bekenstein-Hawking formula, which is saying that the entropy of the interior is getting smaller and smaller after a while as it evaporates. And of course, if we included this enormous number of states, then the state would still look pure, right? So if we can understand the mechanism why the total entropy of these, you know, states with enormous throats is actually bounded by the Bekenstein-Hawking formula, will automatically get a pure state in the Hawking evolution. Okay. Now, there are kind of two. I sort of see two possibilities, and maybe the full answer involves both of these mechanisms. There are two things that could change this answer. We think this is a wrong answer, this infinity, or this infinity, which is like growing with the size of the interior, seems to be a wrong answer. It certainly contradicts ADS-CFT, and it would contradict the Bekenstein-Hawking formula. One possibility, which is kind of the Lorentzian translation of what Julian and Jamie just discussed, is that there might be null states. And maybe actually, I think they both mentioned, both mentioned something along this line. So, but in this kind of more gravitational language, the idea would be that along some spatial slice, like these red lines, you parameterize it by the gravitational variables, like the size of the slice, together with some state of the matter fields, and also gravitational fluctuations, etc. You naively thought you fixed the gauge because you demanded the slice to be, say, maximum volume. That naively locally fixes the temporal gauge. But maybe there are non-perturbative ambiguity. It's like the Gribov problem. It might be that there is still a non-zero amplitude between two different such states. It's not just, the inner product and just the delta function, because there could be some gravitational instanton drawn in this cartoon by this orange blob attached to the slice in between. So this is just supposed to compute the overlap of the state on the lower slice with one on the upper slice. And sitting in this blob, there might be some over topologies or some UV stuff or something that one doesn't know a priori. And the replica wormholes are basically an average over this situation, because if I have, say, two copies of this state overlap question, then I could connect one side to the other side with a replica wormhole. That looks non-factorizing or illogical if we had a single theory, not an ensemble average. But somehow this replica wormhole is computing the average effect of these orange blobs, kind of according to formulas that Julian and Jamie already discussed. Now, what we don't know is the particular way in which an actual UV complete theory, we don't know how to do the full off-shell in a UV complete theory that leads to no disorder, but does lead to these null states. Oh, let me finish the point about the null states. So these kind of diagrams tell you this inner product isn't just the delta function, but in order to be compatible, in order to solve the entropy puzzle, it would have to be that the corrected inner product tells you that the vast majority of the states are null states. And the only states that remain obey the Bekenstein bound. So of all of these states whose number is growing with the interior of the lens, most of them are redundant repackagings. Now, something that's not completely clear in this picture, this diagram looks kind of like a Euclidean computation. And it's not really clear to me whether in the actual UV complete theory where you could do this off-shell path integral and find an answer that works like this, which we don't know how to do, whether there would be a more Lorentzian picture of the same process. So, of course, it could just be that in the Lorentzian geometry, it might be that there are many maximum volume slices starting from the same time on the ADS boundary, some of which are enormously long because they look like highly bent in the interior. So that's logically possible. And I'm not sure if it works like that or if it's somehow a bit more Euclidean. I would say, another thing related to these replica wormholes. The kind of classic geometry, which is like this double trumpet, which contributes to the square of the spectral form factor. In theories like JT gravity or pure 3D gravity, where it's possible to do off-shell path integral, then one finds this non-factorizing contribution. But I think it's an important question. In which cases are there non-factorizing contributions that come from stable on-shell configurations that are in the domain of validity of the effective theory? So in other words, if we think of our gravity theory as an effective theory, where we don't know how to do the exact path integral, we don't know how the theory looks in UV, for example, we only really trust Euclidean path integrals if they look like saddles, stable saddles in the domain of validity of the effective theory. And this double trumpet doesn't really, the double trumpet of JT gravity isn't really like that because it's an off-shell thing. But interestingly, if you had, suppose you did something to your theory, so it was a JT prime theory, where you had an on-shell saddle that looked like the double trumpet in the domain of validity of the effective theory. So in particular, that means not this so-called double cone geometry that's sometimes discussed, because that has a conical singularity, and so you don't really know what happens there unless you know the UV. Like, you need to know whether there are heavy strings that might wrap this region or not. But if you had a double trumpet that was an on-shell saddle with some finite size of the neck in the domain of validity of the effective theory, well, what's the Lorentzian meaning of that? Well, we take the analytic continuation of that double trumpet to Lorentz signature. It looks like this eternally traversable wormhole of Melda-Sena C. And if you really had that in theory without having introduced any interaction between the left and right boundaries, it means that this theory has Lorentzian wormholes that are achronal. So it has time machines. Probably if you have such a configuration connecting the two boundaries as an on-shell configuration, you also find the interior of the space-time. So I think it's very likely, I don't know proof, but it's very likely to me that gravitational theories that allow, Euclidean wormhole saddles in the domain of validity of the line energy theory without having any explicit coupling between two sides admit time machines. So maybe there's something, maybe we don't think that that's likely to arise. And if you do an explicit averaging, then of course you can get such a saddle. So in fact, I think there was a paper of Douglas Stanford in the past year that discussed that. So, and one example is exactly this Melda-Sena C setup. So you turn on a source for some other operator, you couple the sources on the two sides. It's like you do a little bit of averaging of the spectral form factor. That's exactly the Euclidean continuation of this Melda-Sena C setup, and then you get an on-shell double trumpet. So maybe what I'm suggesting is you can kind of, you get Euclidean wormholes where you want them, and you don't get them where you don't want them. So if you did the full path integral in a situation that should factorize, everything miraculously cancels out. But if you do explicit averaging, then you receive these contributions. And I think it's similar to what Julian and Jamie were suggesting. But maybe focusing on this question of which things are actually saddles could be an interesting angle. The other thing I wanted to say is another possibility, right, is that when you do this computation here that looks like the trumpet type computation that leads to this entropy puzzle. Here I drew the same thing, which is like a disk with a hole in it, same configuration. It could be that there's a Euclidean duality. So it might be that when we do the Euclidean path integral, the redundancy in the Euclidean computation between configurations like this and this disk, which is the cartoon for the Euclidean black hole. So this sort of, it seems to be a slightly different possibility than this null states on the left side of the slide here. And maybe there's an interplay between both of these situations. I think for the extremal black hole, it probably has to work more like this situation of the duality on the right. But then there are still all of these semi-classical states. Something has to eliminate them. That's probably through this null state. So there might be some combination of these two. So I think would be really interesting to understand, you know, I would kind of interpret some of this story as a condition on the UV completion or the UV of our gravitational theory. So if we have a gravitational EFT and you UV complete in an arbitrary way, like you put some cutoff, make the theory finite, then you'll find that the dual looks disordered because it will lead to non-factorized answers. And in very special theories, for quantities that from the boundary side should be factorized, it does cancel out exactly and it looks factorized. And then you still get the Euclidean wormholes if you did explicit averaging. And the Lorentzian meaning is that you get these null states. So that was kind of the story here. And I think it would be amazing if we could either find an example where it really works like this, or somehow understand whether this is indeed the right picture or not. Okay, now I'm going to totally switch gears. Here's a second question. This is more of a question. I have less to say about the answer. When we discuss ADS-CFT, we always, we always have as a sort of starting point the boundary theory. That's great. It's an example of quantum gravity where we can sit outside the quantum gravity system. We can imagine an observer sits outside with just the CFT realized on a material in the laboratory, and the experimentalist in the laboratory can measure different operators and so on that look like the operators of any pursuit for Young Mills or whatever the dual theory is, that's like K model. What's not very clear is what is the experience of an observer in the interior in the language of the dual CFT. And I think if we understood the answer to that, it would help us a lot in formulating quantum gravity and things like the sitter space or other backgrounds where we don't have this view from the outside as we do in the ADS box. And maybe to make it a little bit more precise, whenever we talk about a measurement in quantum mechanics, what we really mean, if we see the measurement as a dynamical process, is some kind of interaction between a system and an apparatus. So it schematically takes the form of a product of an operating system and operating apparatus. And then there's some decoherence in the apparatus, and we abstract this process as eigenprojection on the eigenstates of the system operator. So we say we're measuring the operator O system. But the funny thing is that in gravity, there aren't any localized diffeomorphism invariant operators at all. So the measurement Hamiltonian is perfectly localized, some kind of interaction between a system and apparatus. But if we try to split it up into a product of an operator of the system times an operator of the apparatus, there's no nice way to do that because you'll be required to frame the system operator somewhere like the boundary of ADS. And there's many ways to do that, right? It's sort of like there will be a Wilson line connecting the system to the boundary and the apparatus to the boundary. They cancel out in the measurement Hamiltonian. but they don't cancel out in the system operator itself. So one, it seems like an ambiguity, but even worse, it's just wrong. Because if you actually did eigenprojection on a system operator, which is framed to the ADS boundary, it will never commute with the ADM Hamiltonian. And so it would mean that an observer in the interior who makes a measurement can, detectably change the energy measured at asymptotic infinity, which I think is clearly nonsensical. So, or it's just an incorrect description of the system. It's not a good approximation to the system evolving under the total Hamiltonian that does the measurement as a physical process. So I would say we don't really understand the resolution to this. It sounds like something outside the standard framework of quantum mechanics. The way to abstractly describe the measurement of an observer in the interior is not, there's kind of an irreducible error to reducing it to eigenprojection on any operator. And I think this issue is kind of related to why in constructions that try to find operators that act on the CFT Hilbert space, whose correlation functions and properties match those expected from operators of the bulk effective theory, that these constructions always end up having some unusual dependence on the state. So either on a choice of subspace or on a choice of state, which, if one takes it literally, means that they're not linear operators. Now, it's not completely clear to me how state-dependent operators solves this issue of that any operator in the interior fails to commute with the gravitational field very far away, which is sort of physically unacceptable. But it seems to be that the hint that there's we really need some different framework to describe the bulk observables. And I think ADS is a great playground to understand it, because at least we do have the ordinary operators that live on the boundary of ADS, the CFT operators, which are sort of strictly defined operators. And maybe from that we can try to understand the answer to this sort of seemingly puzzling conceptual question. I would say, in de Sitter space, the situation is much more extreme, right? In de Sitter space, the total Hamiltonian is zero. It's a strength equation. Nothing ever happens. So how in the world do you approximate no evolution as eigenprojection on some diffeomorphism invariant operator in de Sitter space? Will have to be a completely delocalized operator. It doesn't seem to, so it's very hard to understand. So somehow in de Sitter space, you don't have the analog of the boundary where what's going on, and you only have this other part that we don't really understand yet. So I think if we knew this, it would help us a lot. And that's the second question. And then the third question has sort of totally different flavor. I have to say these three questions are very idiosyncratic, but I feel like there are three things which I feel like if we understood the answer, we really learn a lot. So the last question is, which gravity plus matter effective theories in ADS have a UV completion? And this also has some relevance to the first point. One of the criterion is that they should, lead to non-disordered theories, perhaps. And we would love to know the answer to this question of what gravity plus matter effective theories have a UV completion of, sort of good quantum gravity theory, whatever exactly that means, really in de Sitter space in our universe. But maybe as a warm-up, we try to understand the answer in ADS. And in an ADS, the ADS CFT dictionary translates this into a very sharp question about CFTs, which is I can start with the generalized free theory, which is a CFT that's defined by having all the correlation functions factorized through Wick contractions to two-point functions. And I can take such a generalized free theory together with 1 over CT perturbations, where CT is the normal two-point function of stress energy tensor. Any GFF or a perturbation around the GFF only really lives at CT equal to infinity, because otherwise the stress energy tensor itself contributes, and if it contributes in so anyway, the point is that the 1 over CT perturbations around GFFs always satisfy crossing symmetry. in fact, it's equivalent to the study of effective field theories in ADS, as first pointed out in the paper of the HPPS. It's worked since then. But we might ask, so the CFT question is, given such a 1 over CT perturbative GFF, so to speak, generalized perturbative theory, I guess I should call it, which of those are completed to finite CT CFTs? Most of them, or extremely rare? And we really don't have any idea what the answer is, but that seems like the kind of question that could be tagged from CFT methodology. And if we knew the answer, maybe it would give us a strong hint, right? The answer tells us, at least in ADS, whether most EFTs are in the swampland or in the landscape. You know, the dichotomy is whether most of these 1 over CT perturbation theories are very close to some finite C CFT, and there are an enormous number of finite C CFTs with a very large CT, and it kind of sporadically covers the space of effective theories. That's like most things are in the landscape. Or alternatively, the vast majority of these theories are totally fake. They are not largely approximates of, you know, sporadic series of finite C conformal field theories, and most of it is in the swampland, and the only very special ones are ones that satisfy special criterion that wouldn't be obvious from the EFT point of view. And we don't know the answer to this in question in ADS. Maybe with CFT techniques, the answer could be understood, and perhaps it's not clear, of course, whether the same answer would be true in de Sitter, but maybe it will give us a hint of whether most EFTs have of gravity plus matter have UV completions or don't. So that was the third question I wanted to pose. So that's all I have, and I hope we can maybe talk about some of these things during the discussion portion.
Certainly. Thanks, Daniel. Very interesting points. And again, maybe we can pause for a few seconds if there are any immediate remedial questions. Yes, I think also it's probably a good idea to have a longer discussion afterwards. So then the last contribution to raise some questions and to you know, give perspectives is Erik Verlinde. And so Erik, if you're ready, I think you can just start.
Yeah, let me see. You can see my slides?
Yes, and it's full screen. It looks good, yeah.
Okay, all right. Anyway, I'm going to just make some comments, more of a general kind, I think. Well, of course, the very important question of how to think about holography in more general context. Of course, here we're discussing ADS CFT. So what I like to do is sort of summarize from my perspective a bit what I find, well, first of all, special about ADS CFT, which kind of may not be generalizable, but then also emphasize those aspects that I think might be more generally true. And these involve developments, not just of recent years. I think we have made quite a bit of progress in reformulating ADS CFT in a language that involves these notions of entanglement entropy and quantum information theoretic concepts that I think capture some of the essential parts of what a microscopic theory of gravity would look like. Anyway, what makes it works better? I think it's indeed the fact that there's a space-like boundary, and which is sort of infinitely redshifted with respect to the interior of the bulk. That sort of decouples the gravity very nicely, and then it also works sort of magically that the dual theory, which is kind of the microscopic description, is also a local quantum field theory. I think that's very special of ADS CFT, and I don't think we can count or think that any other dualities of holographic theories might have the same property.
But sorry, do you mean time-like boundary?
Oh yeah, sorry, it's time-like. Yeah. Sorry about that. Yeah, it should have been time-like.
Yeah.
Anyway, the time-like aspect is very special, as well as the fact that the UV in the CFT is actually the IR in the bulk. And the other way around may also be true, actually, but although it's not so clear. I mean, if we want to think about the short distance property of quantum gravity, it's not so easy to see how that is contained in the CFT, and might be sort of related to sort of non-local aspects of the CFT. Anyway, so what I want to say is indeed, what are the generic properties of ADS CFT that might also apply in more general context? There's actually a question that I think, Julian and also Jamie talked about slightly differently. I do think that ADS CFT is not really an equivalence between two microscopic theories that either are on the bulk or on the boundary. I think there should be only one microscopic theory. And there's some sense in which it either lives on the boundary or in the bulk, on how one looks at it. But you may also think about it as it doesn't live in neither of those spaces, because in a certain way, a CFT is quite a bit of a different animal than most quantum field theories, because it has operators of any scale, and if you just associate the scale to your operator, you might actually argue that even the CFT lives in a space that's bigger than just the boundary. So also, I think the correspondence that we're talking about is one between a gravitational theory, which I think only makes sense in a semi-classical sort of more state-dependent language. So I think the correspondence that we're trying to sort of take over to other space-time should be one in which we can think about semi-classical geometry and the effective field theory that we described in the bulk with some special set of states and maybe operators that are subspaces of the or subalgebras of the microscopic theory that live that we then have as sort of the dual description. But that is really the microscopic theory, and the macroscopic gravitational theory should then be seen as an effective one that arises after a certain amount of coarse graining. And that could be involving this averaging or some other approach. But then the duality is not one between two microscopic formulations that are both sort of equally valid. So let me indeed indicate why I think that this correspondence, even in ADS CFT, is kind of restricted. So normally we can think about the correspondence in terms of boundary fields and so on that we can connect to operators. But this is a perspective that if you just replace the boundary theory by just the microscopic theory, you can try to emulate in other contexts as well. If you simply say, well, there is a microscopic theory that has an operator algebra, and whatever low energy fields I have that do obey the equations of motion, I can associate to variations of those fields some operators in the microscopic theory. I think that property might be valid even in other theories than in ADS space. And then there's even a nice correspondence that was found in the context of ADS CFT that I think might be general as well. Namely, if you then parameterize your states by acting with these sort of low energy operators that are part of the microscopic theory on your preferred state, so you start from a particular state that has some semi-classical geometry you want to perturb around it, then you can look at the family of states around it, and then you can ask questions about things like the Berry curvature that arises when you go around in your parameter space of your classical fields. And that Berry curvature actually translates into a bulk quantity that we call the symplectic form, which if you would use that to quantize a theory, would be sort of like semi-classical quantum theory of gravity in the bulk. That kind of language, if you write it in the right form, actually doesn't require you to talk about boundary or things like that. I mean, it's just a correspondence between the microscopic theory and the macroscopic theory that describes the gravity fields. And some of this can be valid if we don't think about these operators as being sort of part of a quantum field theory, but just more abstractly in a quantum mechanical theory. Then this can actually be taken over in other space-time as well, because as we know, the gravitational equations and a lot of the low energy effective field theory doesn't really depend so much on a strong form on the sign of lambda. I mean, there's a lot of similarity between how gravity works in ADS or in other spacetimes. Another way of thinking about the duality and where it becomes a little more interesting is to think about spacetimes that have horizons, or where we can divide up the space into two parts. And the question is, can we do something similar in more general settings? So the duality is something like that. If you have subregions that are separated by a horizon, then microscopically, we believe there must be commuting subalgebras of the microscopic theory. So they're operate algebras that, when you define its commutant, that is actually something that commutes with all the operators in the algebra. You're sort of imposing that the commutant of the commutant is also equal to the original algebra. Then you have a way of splitting the algebra basically as a product of two commuting subalgebras. And that leads to a picture that you indeed have two spaces, parts of space-time, that don't commute with each other, or don't communicate with each other, which therefore you can think about as having a horizon in between them. Well, we know how this works very well in ADS CFT. We can do this, for instance, for a Rindler horizon. But just more abstractly, we can start just from the quantum mechanical theory that has this property that I have two commuting subalgebras, and then you can define notions like entanglement entropy, even, by the way, in terms of the algebra. You don't really need a state to do that. There's some, well, you have some reference state, but it doesn't really require you to factorize the Hilbert space. Maybe I should say it that way. But if you have a global state, you can define entanglement entropy in terms of algebras. And those are notions that we can try to sort of generalize maybe in other contexts. And even this idea of a modular Hamiltonian might be possible to introduce in that area, in that language. And then you can even, well, think about, well, time flow more microscopically as being generated by this modular Hamiltonian. I think that language is something that we may hope to sort of take over from ADS-CFT to other spacetimes as well. And has actually been used in some contexts, and maybe even in de Sitter space, it might be a way of thinking about how we should describe time flow. An important property of this modular Hamiltonian, microscopically, by the way, is that it has some thermal aspects to it. Actually, this commuting algebras that I have can always be brought into the form that, well, if you write down the state corresponding to that, there's something called the GNS construction, that if you write down the state that you started from, it kind of always looks like the thermal field double. It has the property that if you act with one operator on the right, there's a way that the operation that you have on the left is related by the modular Hamiltonian in such a way that if you write down the state in a certain basis of operators, it will exactly look like the thermal field double. It's not something that you need to impose sort of from the CFT side or from the microscopic theory. It's something that you can derive even just quite formally. And I think it's again a property that might be much more general than just what we know about in ADS-CFT. In particular, we can look at other configurations. Here we had a horizon that is kind of clear. It's a Rindler horizon, but here we have thinking about, say, a black hole. But then we think about the black hole not as something that has a thermal field double, but say as a typical state. And you can do this in the CFT, but just generically when we have a microscopic state with a certain spectrum, then the spectrum may be quite chaotic, and then you may actually think about this linear superposition as a typical state, and you may wonder indeed about the existence of the interior of this well, typical state, because of course it's going to be a black hole, and then we're wondering about how to construct this. And actually in this case you can also define this same structure of these two commuting algebras. So the equation I wrote down on the other slides actually also can be proven to exist actually in this context. It's something that Papadou, Dimas, and Ajou, I think, first emphasized, but We used it also in a paper quite a while ago to sort of emphasize that we can construct or actually prove that there is some interior geometry in these contexts. And actually, again, this language, or the methods that we're using in this did not rely too much on specific details of the correspondence. One thing that I want to kind of emphasize is that if you think about a black hole as being indeed an object with a density of states that is well, rather large, in the sense that you have many states sort of closely packed and have some chaotic spectrum, then the temperature that you derive from this black hole is just well, read off from the density of states by taking the ratio of two of those well, the density between two levels that are separated by a small separation omega. Then this quantity determines the temperature, but it's not like we are dealing with a thermal state in itself. It's basically just a temperature that's described microscopically or derived even microscopically from just the spectrum of states that I have. Still, we believe that if you fall into this object, and that's exactly what we showed in this other paper, is that the experience of someone sort of falling into the object will be like that of someone passing through a horizon. And this sort of indicates more about what is actually required to have a space-time kind of emerging, because in this case, actually the states that you start from are only sort of defined on the exterior, and even the algebra that you have to operate on are the particles that are sort of, well, around the black hole outside of its horizon. But then someone that falls in will indeed have the experience of those passing through this horizon because of the thermal nature of this, this state. And so there is a way in which I already indicated, which is this a GNS construction that tells you that when you have a typical state, that you can make an algebra of low energy operators for which the state looks like the thermal field double. The crucial aspect for this actually is that there is something like thermalization. We make use of ETH quantity, and that there is a notion of scrambling. Actually, it is actually necessary to be able to even traverse these, well, regions, to have that the information that is thrown in indeed is mixed over all of the states in order to sort of be able to retrieve that. Actually, this is something that is well known in the black hole context, but of course it's true for ADS CFT, but probably also something that we can apply in more general situations. Indeed, this is what I just alluded to, namely this idea of the Hayden-Preskel protocol, that if you have a thermal state or a random actually state with a lot of entropy that's being entangled with its radiation, that the notion of scrambling is what allows you to have anything that being thrown in eventually also retrieved. And you may actually here indeed wonder about the experience of someone falling in, or whether indeed it has been sort of, well, decoded from the radiation. I think there's sort of two descriptions appearing here that are kind of dual to each other, that you can either take the perspective of this microscopic theory on the boundary, or yeah, actually maybe I should backtrack here a little bit. I mean, I can think about the black hole states in here in this picture as being, say, the CFT. And one thing that sort of I think we have learned in the recent years is that there's sort of a generalization of all the things that we do in CFTs. If we think about an external system like a heat bath that we couple to the CFT, and then this story of well, falling through the horizon and maybe even entering the inside actually is something that then corresponds to, well, describing the inside of the black hole in terms of the radiation. This is the ideas of islands and entanglement, which reconstruction that we can generalize actually away from just the ADS-CFT correspondence in more general settings, where we have also a microscopic part of the microscopic theory involving a much more well, complicated or maybe even different kind of system that's describing the radiation. There's no reason yet here why the correspondence would fail if the radiation would not be a strongly coupled CFT in this context. Because one of the things that we learn here is that when you throw in something in the horizon and it gets scrambled, then indeed there's the experience that it may fall through and can be decoded in the radiation. And I think this actually is a more general concept that we can think about as what happens actually in space-times more generally. So indeed, I actually think this same mechanism that allowed the Hayden-Preskel protocol actually applies even in ADS-CFT. So the question I'm going to be addressing here is, take ADS-CFT as we normally know it. I'm going to think about the description of the bulk, but from the perspective of two observers that have only access to half of the CFT. So we are actually in the context of a horizon where we have split the Hilbert space into two parts. And there is a particle that one observer wants to sort of emit from the left to the right. So without any time evolution yet, I mean, there's just the two sides, and there's no communication possible yet, because that's in the pure Rindler situation. The two observers are disconnected, but nevertheless, it's possible to have a particle going through from left to right. Now, you might ask, well, this is just simply just allowing the particle to move through the bulk and arriving on the right-hand side. I think, but what microscopically is happening is that there's two regions that are first not communicating. Those are the regions A and A bar, and sort of they extend over these causal wedges. And I want to have a particle that goes from A, say, to B bar, because that's sort of what a particle would do that would cross in here. And then there's a time step that sort of is involved in here, but what I'm claiming here is actually that this time step will act in a very similar way as the Hayden-Preskel type protocol or a quantum teleportation step, in the sense that the information that allows you to reconstruct the state that is describing the particle before it crosses the horizon and afterwards is not being transmitted directly by taking the state and moving it. The actual information that's being transferred is actually a little bit on the boundary, which is a time step, but that allows you to reconstruct the state on the other side by making use of the entanglement that we have in the space-time. And I think this picture, which is kind of a local picture in the bulk, is something that I think is generally applicable in space-times. If you ask what is really making the space-time connected and allow particles to move through it, it's something that we learned also in these traversable wormhole scenarios that Daniel and his collaborators worked on. It also, there, the story is that there's some communication between the two sides that sort of is only, well, sort of a classical kind that allows you to have particles traverse wormholes. And actually the same is actually true, I think, in this whole, well, way in which we can propagate through the bulk. And so I think the entanglement is precisely required to have a connecting space-time, because motion or just having signals go through is actually a form of teleportation, which is well known, needs some form of entanglement. So this is the lessons I'm learning from ADS-CFT that I think are more generally true and can be perhaps taken over in constructing models of other spacetimes. Maybe just to elaborate a little bit more and clarify a bit more why I think this is a teleportation step. I have one last slide. So if you think about what is allowing a particle to move from one side to the other side. Normally we think about a particle as being associated with a certain region. So this particle is on region A, and this is a particle on its complement. But there is also ways of transferring particles from one region to another region in a way which is called sort of quantum secret sharing. Namely, it's indeed the reconstruction of space-time that requires you to have more than half of the space in order sort of to have something, or the region to have something that's, say, in the middle. So for instance, A and B can reconstruct this one. So if I do this in this story here, if you ask what is really being transferred in a time step when a particle is being, well, going from a entanglement with region, which is yellow and blue together, you want to go to the blue and green one. It's kind of exactly the same as I have here. It's basically that when you just transfer this little bit of information, which is near the boundary, from the left to the right, this is actually what allows you to reconstruct the state without having actually transformed the state itself. You basically have allowed the wedge sort of to have a little bit more of information, because it's neither yellow nor green that can contain this information, and even the blue part doesn't contain the information in here if near the boundary. It's only when you combine two of those that you can reconstruct those particles. So anyway, this is what I think is why this idea of, well, that motion is something like teleportation is something that we can even test in ADS-CFT, but I think it's something that is more generally true. Anyway, these are ideas that I'm having about what we might learn from ADS-CFT that we can maybe use in other values for lambda. All right.
Okay, thank you very much, Erik. That's also very nice to have extended the set of ideas in another direction. So yeah, so in the interest of having a discussion, I mean, so I do have, like, I wanted to make one comment and maybe also point out some commonalities, but there was actually just one technical comment which is related to one of the questions I asked. So it was actually stated that we have an example where there is really a matrix model that describes gravity, in particular this JT, which is dual to a matrix model. And I wanted to just point out that in my opinion, this is not actually entirely correct as such. So of course the paper, the beautiful paper of the SSS and this work of Mirza Khani, that's all correct and very nice, but it only shows this equivalence at the perturbative level of the matrix model. And in fact, for a lot of the interesting effects that we all actually talked about, you really need the non-perturbative sector of the matrix model. So I'm just saying that this is a little hint that, you know, I wouldn't count this as a smoking gun example, that even there exists such a theory that is, you know, where we have the duality established, and so that gravity really is an ensemble. That's just a technical remark. And the other thing, I mean, maybe I'll invite other panelists to comment on what they think as well. I thought there was some very interesting suggestions of commonalities between what we were saying, and in particular, the idea of having some sort of, I mean, it was raised by Jamie first, but I think it was implicit in what other people said as well, that somehow we do want to do some coarse graining in order to get semi-classical gravity. And the question is, what is that coarse graining? And as Erik pointed out, and Jamie and also Daniel, that there seems to be this idea of, you know, having some idea of complexity which comes in there. And so I think the idea of sort of how complexity interacts with this, could there be some complexity RG that gives us the effective field theory? I think that's something interesting to ask as well. And I can certainly see some interaction, for example, between this RG, well, this effective theory that we talked about, and complexity. But right, so I don't know, does anyone want to say something about this comment about the matrix model? Maybe I'm being too critical. So I suppose we agree with that.
Now, I actually say, I thought that for these minimal matrix, minimal models, people have also non-perturbative ways of addressing those that do see the two settles that you're talking about. I mean, it's not like matrix models have only one perturbative expansion, do they? I mean, is that what you're saying?
No, but what I'm trying to say is that the gravity theory itself, JT, at least from the gravity perspective, we can only recover so far the perturbative sector. Right, so we don't know
that
whether
is correct. Yes.
What do we need to do with JT in such a way to recover the non-perturbative corrections? And at this point, the story is, the question is still open. We don't actually know.
That is true. It seems like you need to add something there that is also non-perturbative in some way, which is not automatically contained in the JT gravity theory. That's correct.
Yeah. So I just wanted to, I wanted to make that comment. I don't know if this has a particularly deep implication for what you wanted to say, Jamie, but it just struck me.
Yeah, I mean, I think maybe to speak to the question more generally, then, and how do we distinguish between, say, coarse graining and ensembles, and what are the types of observables or ways we might try to see if one is a better description or the other? I don't know the answer to it. I don't know that I have anything very insightful to say about that.
Yep. Thanks.
So how do you define coarse graining differently from ensemble leveraging?
Yeah, so that, okay, I think that's also a point that we should discuss. So, but maybe Tom Hartman has actually wanted to make a comment maybe on this, or
sorry, I have an audio problem. One sec. Okay. Yeah. I agree with your comment, Julian, and I wanted to add to it to say that more realistic theories of gravity are more similar to JT gravity with a cutoff on the dilaton, say at phi equals minus S naught. And so even if the dilaton integral that's been done is fully non-perturbative, it might be it might be more realistic to put that cutoff, and then we would expect to have corrections to that story.
Yeah. So yeah, again, somehow this seems like these seem like technical comments, but I think it is important because they put us in the situation where also Tom and I recently had this exchange in his review that we don't at this point seem to have any particular evidence that we really are forced to accept that gravity should be an ensemble. So far, everything might be reconcilable with, you know, one theory. Of course, you know, Erik's comment being well taken, but that wasn't about whether in principle there is one theory. It was just whether we should think of boundary and bulk as two different single theories. Daniel,
yeah, two comments about that. So I mean, one of them is like in higher dimensions, I think we don't really expect that there exists continuous families of CFTs, or certainly not families with a dimensionality of order e to the s, right? Maybe there's some low dimensional families, but we don't expect that we can just, you know, move around the dimensions of high dimension operators in a continuous and arbitrary way and beyond quantum mechanics. You know, of course, in quantum mechanics, you don't have any constraints, right? But in higher dimensions, you have, if you took, you know, n equals 4 super Yang-Mills, and then I adjusted the energies of the high energy states by a little bit, it won't satisfy crossing for heavy operators among themselves, which would mean that the dual theory in ADS looks like it will be like a non-zero commutator between operators that create black holes that's, you know, all the way out at the ADS boundary, which sounds sort of infinitely non-local. So of course you could have an ensemble that's, you know, a discrete ensemble over some sporadic list, but I mean that in a discrete ensemble, it means that you can tell which element of the ensemble you're in with a finite amount of measurement. So it seems to lose a little bit of the spirit of an ensemble somehow. But yeah, I mean, the other thing I want to say is I wonder whether an important aspect is on-shellness of the configurations, right? So, I mean, it's very special to be able to do off-shell path integral exactly. And it might be that, you know, so in other words, like suppose, you know, if we thought that there was an off-shell description of the gravity theory, which isn't even completely obvious, right? Like we don't have off-shell description of string theory except through string field theory that we don't.
Yeah, that was one comment. I mean, yeah.
And I mean, but even if we think we can make perfectly well-defined an off-shell path integral, say in string field theory or something, we might guess that it was the kind of path integral whose answer is exactly given by, sum over resummations of the perturbative expansions around the saddles, like through resurgence or this Borel resummation. And then that might be, in a way, a mechanism to understand why certain kind of saddles can contribute to quantities with explicit averaging, but they cancel exactly when you don't have explicit averaging, which sounds like very puzzling from the point of view of the off-shell path integral, but maybe sometimes you have a saddle and sometimes you don't have a saddle. So I think we know if you do explicit averaging, then you can get Euclidean wormholes as saddles. And so those will never, those which are the things we really want, right, will never go away in any reasonable gravitational theory. Like a good example is take the square spectral form factor, and then each one of them we add some light operator with a constant source. So it's like we study trace of e to the minus beta h plus j o, where j is some small source, and we do that on both sides. And then we make a small averaging of j around j equals 0, for example, the Gaussian. Well, of course, then we can just integrate out j, and it's exactly the same as studying the combined system of a Hamiltonian h left plus h right plus o left times o right. And we know that Lorentzian setup has a Lorentzian dual that's a smooth saddle that looks like this Meldesinic C geometry, whose Euclidean continuation is the double trumpet. So there when you do something like that, there is a saddle, and the saddle is supported by the one loop stress energy induced by this O left, O right, and it's kind of like this traversable wormhole picture. So those saddles will not go away in good theories, but maybe the ones that seem more puzzling, which we really only understand from off-shell path integrals in very special theories, somehow don't persist. I mean,
So are you proposing in some sense whether a given contribution is an exact saddle or not as being a distinguishing criterion between something that fundamentally is an average theory and something that fundamentally is not, but maybe has some coarse-grained description that looks like a...
Yeah, something like that. I mean, this idea isn't completely perfect because there do exist saddles, say, of pure 3D gravity where you have two higher genus boundaries.
That's right, exactly. Yes.
But I mean, maybe somehow in the physically correct theories, those saddles become unstable or go away in some form that I don't quite know what it is.
So that would have to be the case, right?
It's a speculation, not a result. But anyway, yeah, so it's just a suggestion.
All right. So, I mean, I have questions for people, but maybe the audience also wants to ask, pick up certain points that panelists raised. Yeah, Pranjal Nayak has a question.
Yeah, I have a question for Daniel. I wanted to ask him, when he talked about constraining the space of theories with gravity plus matter fields in the bulk, I think he meant it more than how the constraints that follow from the spectrum of operators in a conformal field theory. Could you say a little bit more about how you meant it?
You mean the third question I asked, or you mean what I just said?
No, the third question you asked.
Oh, okay, yeah, right. So, I mean, in some ways, I think these things are related. So let's suppose that somebody writes down an effective theory of gravity plus matter of different type in ADS. It could be like the low energy, limit of ADS 5 times S5 supergravity plus, whatever part you want to include. And we but suppose it didn't come from string theory. So you just write some random EFT in ADS, and then you want to know whether, is there an actual dual CFT or not? So we can try to see whether the dual will satisfy, crossing symmetries. It's sort of a well-defined bootstrap CFT. And at first, if we just check crossing of light operators among themselves, low dimension operators among themselves, then it will be a solution to crossing in 1/CT perturbation theory. That's kind of the HPPS result, and I think it's been even made a bit more precise and so on since that time. And then we can also, but that doesn't really establish that the thing is a good theory exactly, right? It doesn't say that there's a finite CT theory there, which is the non-perturbative completion of the 1/CT perturbative expansion. And so the question of whether most EFTs are in the landscape or the swampland is kind of whether, most of these 1/CT perturbative theories are, UV completable to some sporadic finite CT theories, or most of them are not. And maybe from a CFT side, we could try to address this question. I mean, I think an important ingredient probably has to come from the consistency of crossing of heavy operators, because so if we look at, say, a 4-point function of 2 heavy and 2 light, then I don't know, but it's possible that could be described by a kind of pH-like matrix model. And so maybe looking at those correlators also, in a perturbative sense, in the 1/, at large CT might still not be sufficiently constraining. I'm not sure about that, but that's conceivable. But probably you really get the strongest constraints by considering crossing of 4 heavy operators. That's the thing that somehow is very hard to satisfy. In other words, if I took n = 4 super Yang-Mills and I monkeyed around with the high energy states, I changed the dimensions and the 3-point coefficients by a little bit, it will not change the effective physics in the black hole background, so to speak, very much, but it will make the thing not a CFT, not a local CFT anymore, because the heavy operators don't obey crossing if I monkey with them in a random way. Maybe somehow it's really that which is required. I'm not sure, but anyway, that was what I meant by this question.
Andres, is a follow-up to Daniel's answer?
Yes.
Okay, and afterwards, Alex Villain also wanted to ask a question, but go ahead, Pranjal.
Yeah. So in this case, for the particular example that you gave about the 4 heavy operators and their crossing, and especially in light of what we have been discussing today, saying that for the sufficiently high energy operators, the physics, at least at the low energies, or the gravitational physics only capture some kind of an ensemble description. In that case, is that even a well-defined question to ask, can I make it more precise what the crossing symmetry for 4 heavy operators means? Because what we are trying to say is just in the gravitational descriptions we can't even probably distinguish operators which look similar from that point of view.
Right. I think that was kind of the point of the question I was trying to pose, which is if in other words, any gravitational EFT that sort of obeys the correct IR restrictions looks fine. And from that, you can determine, the correlators of light operators and the statistical properties of correlators of light operators with heavy operators along the lines you said. But the question is whether that structure is an approximate or a coarse-grained description of some specific CFTs that actually exist, or if most of the time it's a mirage and there isn't any, finite CFT with, fine-grained specific heavy operators, which obeys crossing for all operators. So, and of course, it's very hard you can't really answer that question from the gravity EFT. That's kind of the point, right? The question is there some constraint of UV consistency that looks non-obvious from the gravity EFT? because otherwise all the gravity EFTs sort of are close to some real CFT. I don't know. So I don't know what's the answer. Yeah.
Okay, let's pass it on to Alex, but I also want to tell everybody that, I mean, we still have some time, I guess, maybe because we started a little bit late, but Jamie has an IR cutoff. So if you have any urgent questions to Jamie, I think you should do it now and thereby prevent him from meeting him at his IR cutoff because he has to answer a question. So I would, but I will send, I think I will send you a message, Jamie, also in the interest of your duties. So Alex, what is your question?
Yeah, since we're talking about the space of consistent theories of quantum gravity, I wanted to make a comment. We often say that what we want is start from GFF and you know, do 1/CT corrections from that. And that's fine if we're considering theories of quantum gravity where the matter sector interacts at the Planck scale. But you know, at the end of the day, the questions that we would probably also, since this is an all lambda workshop and we're trying to make connections more with the real world, the type of questions we would really like to understand is, you know, how to take a strongly coupled QFT, something like the standard model, and then, you know, consistently couple it to gravity. And so in that case, we would not have to, we could not start from a GFF. We would have to start from something that's already describing like strongly interacting matter. And somehow that hasn't really been studied too much, probably because it's hard, and probably also because, you know, the top-down constructions we have do involve matter that interacts at the Planck scale. But I think it's a really interesting question for the field to try to tackle that. I'm not sure exactly how, but something that we should be thinking about.
Yeah, I agree.
All right, so I don't know how we should proceed. I mean, it depends a bit on the local.
Can I ask another question? I don't know if we have time, but
Yeah.
talking about, you know, crossing of heavy operators. So what if I engineered a situation where, you know, 4-point functions of heavy operators are not exactly crossing invariant, but somehow if you start averaging over the heavy operators, then it becomes crossing invariant. Like the mistakes you make average out somehow. What would we call that? So that's still not a definite CFT, but it's better than a case where these mistakes don't average out. Is that kind of like what we're looking for somehow?
I don't know, but my guess would be that if you allow things like that, then you will not find any constraints on low energy physics at all. So you'll be able to, in that sense, any EFT will be good. Like, in other words, you could take an EFT with some arbitrary kind of short distance cutoff, like a hard cutoff or something. And imagine doing the exact path integral of this cutoff theory. Then you'll get some answer. That answer probably takes the form you just described, I would guess. And I don't know if we should be happy with such answers or not. I personally would not be, because I would say the theory in the bulk is extremely non-local, because if you take two black holes at infinite separation out of the ADS boundary, their operators don't commute. It sounds terrible to me, but I guess it's a matter of taste or something. But I might suspect that you don't get any constraints in such structures, but I could be wrong. But.
Erik, you wanted to add something?
Yeah, I wanted to say something. I mean, if you have a very heavy state, I mean, why would it correspond to something that you can create by a local operator? I mean, because in operator state correspondence, we generally have a correspondence between local operators in the CFT and states in the bulk. And I can understand this for the low energy particles. I mean, the low mass particles, because those are things you can sort of create by having things going all the way, coming all to the boundary, coming in. But I think for black hole states, I don't see an argument why a black hole state should correspond to a local operator in the bulk on the boundary. I don't think that that is kind of necessary. And then I don't see the reason why it should have satisfy these crossing relations.
So, I mean, I thought the idea would be that no matter what kind of object you have, as long as it has finite extent, like a black hole, then I can translate it with a conformal transformation of some kind of ADS isometry farther and farther toward the boundary, so that it looks, from the CFT point of view, more and more shrunk down toward a particular point of the CFT.
Yeah, so you're down a black hole state to sort of a point-like operator on the boundary, which is kind of what I find somewhat unnatural. Maybe that's what I'm trying to say. But so I don't see the actual reason why black hole states should satisfy crossing relations. I mean, this kind of the.
But I mean, wouldn't it, in other words, if I have any localized object that's sufficiently close to the ADS boundary, doesn't it look?
This I understand, but is there
right?
then there should also be a gravity reason why it should satisfy the crossing relations.
Well, yeah, I agree. It's a little bit harder to think about, but somehow it looks like a mixed Lorentzian Euclidean picture, right? You kind of glue some Euclidean tube in that creates the state or something. Maybe there's a better way to understand that. I'm not exactly sure what it is.
So maybe in view of time, I'll allow myself to say something, maybe, because this was the ADS CFT panel on the all lambdas holography. So I think that what's become clear is that, I mean, there really is a new set of very fascinating questions that are extremely well posed in ADS, and that somehow have raised this new aspect. One might say maybe of topology, because in the end, what is the difference between the way we thought about ADS-CFT before from the bulk perspective and now is that somehow we want to semi-classically include interesting topologies. And that somehow gives us a view onto microscopics. I think that we all somehow revolved around similar questions was maybe not so obvious. I think it might also be an interesting take-home message to try and think about how they connect. So for example, Erik's ideas on code subspaces and whether that is a bulk EFT. One might ask the question, where does topology enter there? The EFTs that I've talked about, well, they're EFTs of ensembles of theories. They give you topology. Jamie talked about EFTs that are more related to ensembles of states. They give you topology. Anyway, I think that there is, well, and of course, Daniel also, I think, raised a very important point that maybe it's worth saying again is, it's also always a good idea to think about the Lorentzian picture. And that gives, new, very important inputs. But, well, I think that we probably should pull things to an end here, but maybe keep this set of ideas in the back of our minds for the other discussions, because some of them for sure, as also emphasized again by Erik, do have their avatars for other signs of the cosmological constant. And I believe that an interesting idea of this conference is to try and have some dialogue. I believe that there will be a panel at the end. So maybe we can all reconvene and see whether we can find some common points with other signs of the cosmological constant. Take away the message today, which is apparently is topology. Okay, unless someone else wants to disagree, I think maybe we can leave it at that.
Yeah, that sounds good. Thank you, Julian, and all the panel speakers.